I want it to be like a ride. I want it to be like a roller coaster.
We wanted to do something more than just create beautiful renders. We wanted to tell a story.
We can simulate years in a matter of days on a single GPU.
And when we calculate how much faster that is, we double-checked because that was nearly 100,000 times faster. So yeah, that was a really cool aha moment.
3.5 minutes, 70 shots at 4K in 14 hours.
It's just mind-boggling to me that we're able to get all these things done in the short amount of time that we have.
GTC is where we come together every year to share our work with the world. And one of the biggest parts of that story is where NVIDIAns and our partners join forces to help solve the world's biggest problems. This year, we decided to kick off the keynote with a video that celebrates this story, using a seamless blend of drone photography, CG magic, and of course, Omniverse.
We try and open every keynote with some spectacle, video or animation that embodies the essence, the spirit of NVIDIA.
When you're first kind of coming up with the idea, you would do a layout and storyboards, and you would show it to the big decision makers and be like, what do you think? And you're kind of loosely describing an idea. And sometimes people think the idea is more than it is, or less than it is, or different than it is. What's nice about Omniverse is we could just take our layout, throw it into Create, and light it, and we could show, like, this is our idea. And it's a pretty good representation of what the final product's going to look like.
I think the biggest challenge that we encountered was timing. We needed to have a lot of successful queues of the robots. And to do that, we needed like an army of NVIDIAns to help us queue these robots, to pilot these drones. So many elements to coordinate. We had a car, we had the drone itself, we had autonomous robots running around doing their own thing in the lobby. We had a couple other robots. Then we had like a Blue Angel kind of squadron of autonomous drones in the back courtyard. So many things going on. It was a miracle that we pulled it off.
We thought that a fly-through of campus highlighting our new building would be a great way to show how NVIDIA is thinking forward, ever expanding, and find really dynamic ways of bringing the campus to life.
Hi, welcome to NVIDIA.
And at a certain point in time, when we turn a hallway and go into an elevator, we transition to all CG.
Using the elevator shaft as this conduit to do that was great, to the point where people didn't even realize they were moving out of live action and into a CG world.
We went into our Omniverse created world. We were also trying to tell the story of what Omniverse is being used for, right? So not only is it being used to create the thing like that we're showing, you see the Isaac training the robots, the Earth 2 sim. We're telling the story of Omniverse with Omniverse.
Omniverse was used at every stage of production from the very beginning to the end, and at times in conjunction with existing DCC apps out there. Our camera and animation department was using Maya to create the camera moves and produce the animation of the vehicles and the robot arms, and sending all that data downstream into Omniverse. Our asset builders were constructing the world in 3D Max and Maya, doing the surfacing and substance, and creating the materials using MDLs inside of Omniverse. The effects team creating the holographic simulations. Those were done in Houdini and also sent into Omniverse. The lighting team was doing all the cinematic lighting, composition, depth of field, and then also rendering the shots out for compositing later outside of Omniverse. The platform enabled the team to be creative, have fun, frictionless, be able to work smoothly together and get the job done.
More than a story, I want it to be like a ride. I want it to be like a roller coaster. I want it to be exciting. I want it to be entertaining. It's the ultimate appetizer to get them ready for what the future was going to be.
Welcome to GTC. I hope all of you are well.
As you can see, NVIDIA lives in this amazing space where creativity and science meet, and Omniverse is no different. While often a focus of GTC itself, our creative teams also rely on it every day to produce their best work. Their latest production, Orchestrated to Perfection, is no exception.
It was a super long product meeting. It lasted like 7 hours. And so I went to my car after this meeting, really tired, and turned the radio, and suddenly Sing 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 is playing, like boom, 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 boom. I saw these DGXs just like acting like trumpets.
David came to me with an idea. He wanted to figure out how to bring the data center business to life in an engaging, entertaining way. He had this idea of creating a music video, where the whole data center would come to life, dance around, and move to the rhythm, showing how the data center is orchestrated to perfection.
The first storyboard, they already nailed it. It was beautiful. It was very similar to what I saw in my head. However, they did contribute quite a bit to the story. After the music was recorded, we did an animatic, sync to the music. And that's what we presented to Jensen. And he loved it, but the one feedback we left from that meeting was the instruments are not fully clear who's doing what.
So we were able to associate each of the hardware server components with one of the instruments in the song.
Before the animation started, we get the storyboard. We use that as a guideline. It gives us an overall view about how all the shots connect with each other. Once we study that, and then we started in Maya, we set up the camera using the storyboard as the guidelines, and then we start animating each of the assets. And then we'll bring in the music, which is a big part of this project. So because all the motions will have to be in sync with the beat. In the dancing chip sequence, I work with Michael in lighting because in this sequence, spotlight or lighting is almost like an extra characters in there.
I worked with Rini on the H100 vignette, so all the dancing chips, and created the environments and gave her the layouts for the environment so she can then place the cameras. And because of the quick rendering of path tracing, we can see things in an expedited rate, so we can easily see the problems and easily fix them.
And anyone who's lit metal objects know that it's very, very difficult to light metal. It's a lot about like putting the thing that it's going to reflect in the right spot. It's a lot of trial and error if you're doing something that's a completely offline render. Being able to see what the final product is in the viewport and being able to move a card to get that perfect highlight on the edge, massively time saving.
If you're seeing an animation where your lights are placed, it may pop when it's animating. So you have to either adjust the materials if you like the lighting or adjust the lighting values just to make sure it doesn't really catch your eye.
After all the animations are done, all the assets are exported to Omniverse.
Omniverse is kind of the hub for everyone working. Omniverse is built on USD, so everything kind of worked hand in hand.
What we like to do is render first, middle, and last just to test and see how it's going to look throughout the sequence without having to wait for long render times.
There was so much rendering that was going to have to be done across multiple teams, multiple projects, that NVIDIA built our own internal GPU render farm, substantial in size. I believe like 1,500 or 1,600 GPU nodes.
I personally, as an artist who's worked on many shows, have never sent to 1,000 GPU render farm before, and it is glorious.
So originally we were going to end orchestrated perfection with an IT woman who was going to walk down the hall. Maybe she heard something going on in the server room. She flings the door open. There's nothing going on. It's quiet, silent. She closes the door, and then the server room comes back to life, and that's how we end the piece.
When we pitched the second review to Jensen had actually a great idea of why not just use TJ? And for those that don't know, TJ is what we call Toy Jensen.
At first, we're like, oh, geez, that's a lot of work.
Most of these shots were already final, so we had to go back and just tweak them a little bit for that particular character.
And he's much shorter, and he opens the door.
I thought it was going to take a couple days, but the next morning, they showed me a completed pass with Toy Jensen replacing IT Woman, looking amazing, and we're like, all right, we got it done. It works. So then we asked ourselves if we could render this in 4K right before delivery with 16 to 24 hours left in our schedule. So we fired up the render farm, sent off 70 shots.
And all those 1,000 machines hungry for rendering say, I want that rendering, and they chew through it.
14 hours later, every shot had rendered, 4K, maybe one or two shots needed some touch-up. It was impressive, the performance of the GPUs and Omniverse in turning around a show that quickly, 3.5 minutes, 70 shots at 4K in 14 hours.
All of these talented people that are contributing to this hub that we call Omniverse, that get the benefit of real-time visualization of what's going on, the contributions of all these different people, is no different from orchestration. And doing great orchestration is hard, no matter what field you're working on. The more people can participate and collaborate, the better for the project. And I believe that output is just going to be way more interesting.
From one data center to another, Omniverse helps bring it all to life. And when it came to introducing our Hopper GPU, we traveled from micro to macro, using billions of polygons, soap bubbles, and a lot of teamwork.
Today, we are announcing the next generation. The engine of the world's AI computing infrastructure makes a giant leap.
For this GTC 2022, we had to announce the Hopper architecture on the H100 GPU.
We wanted to do something more than just create beautiful renders. We wanted to tell a story of how such a small die integrates to such a huge system like the SuperPod.
We didn't want to treat it as a cinematic with different shots. Instead, we wanted to have something very fluid, so we chose to do everything in one gigantic shot.
In a perfect world, to pull off an animation like this, you would need at least 6 months, and that's being generous. We didn't have 6 months. We had about 3 weeks.
Each element of this animation is a complex model that has many thousands of parts. The scope was way more than we've ever experienced, to the point where we had to figure out an efficient way to prepare these models so that the animation could be done. We had to work in parallel and overlap many of the other parts of the creative process in order to hit the deadline. The main animator devised a rig that can easily swap out a placeholder object that he would work on to animate with the real object once it's done prepping.
So now that we have accurate files from engineering, now it's time for the fun part, to start talking about being creative. How are we going to make this aesthetically beautiful?
We had to start with the H100 GPU. It was going to be, after all, the hero, right? The architecture.
We took tons and tons of reference of piano black materials, of soap bubbles for the thin film. We wanted to encapsulate all of these things into this die to make it look as beautiful as we possibly could. We had to make sure that the lighting for the small die was just as consistent as the SuperPod. So light placement, light intensity, all of those things were crucial to make this shot work. One of the great things about Omniverse is how well it handles large amounts of data. This animation handled 6 billion polygons.
This was very beneficial for the creative process. We could get into live sessions with art directors, and then we would make decisions to make sure the materials looked the best they could.
Can you rotate it a bit so I could see a little more dramatic reflection?
We don't have to wait and animate 1,000 frames, render it, have it come back, and then decide whether we need to move a light a little to the right. We can see instantly where the reflections are sitting, where the shadows are casting, all of that in real time. So once the look was approved for the H100, and it was literally at the last minute, at the buzzer, I quickly packaged up the asset and then it was delivered.
Looking back after the animation is done, I'm just amazed at the teamwork and the skills that we have to deliver such a beautiful product. It's just mind-boggling for me that we're able to get all these things done in the short amount of time that we had. There were many, many sleepless nights, but we all pulled together as a team and we did it.
From microchips to planets and the world's first supercomputer dedicated to climate change research, Earth 2. And we just got a glimpse of what Earth 2 will be capable of.
ForecastNet is an AI-based weather forecasting model that we have developed here at NVIDIA. It's lightningly fast and at the same time accurate. It can provide forecasts in a matter of seconds.
By going so incredibly fast, we're able to generate extremely large ensembles of weather predictions. So what that means is we're predicting the possible future of the weather many, many, many times, and that can give you really good statistics over what's likely to happen.
So to train the ForecastNet model, we used what is known as ERA5 reanalysis data.
And what that means is that's data that was predicted by the IFS weather model from the European Center for Medium Range Weather Forecasting. And it's one of the most accurate representations of the state of the atmosphere that exists.
We can make predictions at the resolution of 25-kilometer planet scale. whereas earlier deep learning-based models were making predictions in the range of hundreds of kilometers.
Not only are our predictions very accurate, they're really quite close to the original IFS quality, using only a very small fraction of the data that's available. So we've used just a handful of fields, temperature, pressure, humidity, at just a couple of elevations. And we were amazed that we're able to forecast the weather in 6-hour chunks, like 6-hour giant leaps, with just this very small amount of data.
And when we calculate how much faster that is compared to numerical weather models, we double-checked because that was nearly 100,000 times faster. So yeah, that was a really cool aha moment.
So the forecast net is basically the really fast prediction part of the model. On the other side, you have Omniverse, which gives you the beautiful rendered ray trace visualization of the Earth. And when you put these two things together, you can basically predict the data and see it immediately, so you can interact with it in real time.
Visualization can be used to make the data accessible and digestible by almost everybody. You can run it at home, basically. And that makes it very powerful. It democratizes access to weather forecasting.
But eventually, we're going to couple this to a much larger system. We're going to couple it to a model that basically predicts the climate and then uses that to initialize many weather simulations.
NVIDIA Modulus is a hybrid physics ML framework that can enable such hybrid physics ML methods coming together for different kinds of input data.
We are aiming at going to use observational data, incorporate data from satellites, from ground station, commercial aircraft, to basically create predictions which are much closer to reality.
So I expect even up to 1 millionx speed up in a lot of these processes that can lead to unprecedented simulations and along with it, new discoveries.
And we want to get right down to the perspective of being on the Earth and being able to look around and see what the weather or conditions are like at some deep point in the future.
ForecastNet is just the first step of our ambitious Earth 2 effort, where the goal is to build a digital twin of the Earth.
And the entire point of the Digital Twin Initiative is to attempt to help us forecast and prepare for a very difficult climate future that's coming our way. So in future years, you're going to see a lot more wildfires, a lot more floods, things like that. And everybody needs to be able to understand what's coming to make the right decisions. And in order to do that, you need to make many predictions so you don't miss those extremes.
We want to get accurate extreme weather predictions, and this has huge social as well as human costs.
Digital twins are set to change how we see the world and, together with DriveSim, how we move around it. Our research team is making that easier than ever.
Our DriveSim GTC demo really focused on our ability to create content so that we can test not just the performance of the vehicle in that scenario, but all of the edge cases surrounding it.
We employed 2 different methods to actually reconstruct real-world events and enable them for resimulation. In the first approach, we construct the scenario from real-world data.
We extract this deep map data into an intermediate USD format called Digital Twin GT. We can turn this into anything that we want. If we want to add additional information about the lane lines, is it double yellow? Does it have reflectors? We can add all sorts of information at the USD level, which is natively supported in Omniverse.
Artists create all the content, all the city elements, vehicles, humans, and this allows you to do a lot of great things. However, the artist-created content, it's really time-consuming.
We know that we need to create huge volumes of content, and you can't do it all by hand. So we need to be able to create that volume of content automatically.
The second approach, a neural approach, is just using AI to reconstruct the scene. We're taking an old drive that already happened, that is basically stored just as video, and use this neural reconstruction method, and we're bringing it back to life. We basically separate the static scene as well as the dynamic object. And then we use neural radiance fields to render the background and composite the object back into the scene. We can recompose the scene in a controllable way. So suddenly now we are the creator of the scenario. In that demo that we showed, we kind of purposely swirled it a little bit to the left. We wanted the other cars to react in a plausible way to the ego car. As we continue the demo, we see on the left this car hits this traffic sign, and there's a construction vehicle appearing on the right. What we wanted to show here is we're able to virtually insert objects into this modified drive. Now suddenly this becomes a closed-loop simulation. The main benefit of the second approach is it's a lot less time-consuming for humans. You can just take real-world recorded data and use these neural reconstruction methods to basically turn them into simulation.
So what comes next? I mean, we've talked about digital twins and real time, so you put it all together and have that ability to reconstruct the world at scale. We want to be able to simulate not just one car driving in the digital twin world, but a whole fleet of vehicles that are communicating with each other and interacting with each other.
Wouldn't it be amazing that we can identify any location, pinpoint, and then click, and we would be taken to a digital twin representation of that location, do simulation, training under different randomized variations, and that's where the future is. I mean, this is the holy grail of content creation.
The same research team reinventing how we train autonomous vehicles is also exploring how AI can give animators new ways to create faster, more accurately, and more intuitively.
One of the biggest challenges that we had with this project was being able to train very expressive models that can perform a lot of different skills. For us, the breakthrough moment came when we switched over from a CPU-based simulator to a GPU-based simulator.
So Isaac Gym is a massively parallel physics simulator that runs on NVIDIA GPUs. And this just makes the training of our policies orders of magnitude faster, which is the only reason why this project is feasible in the first place. The fact that we can simulate years of simulated time in a matter of days on a single GPU is just insane, and there's no really other viable alternative.
In order to train our ACE model, we use a dataset that consists of a large variety of behaviors recorded using motion capture from live actors. This dataset shows behaviors that range from common everyday motions like walking and running to more athletic behaviors showing a gladiator character performing skills like sword swings and shield bashes.
And then it gets processed into a format that Isaac Gym can actually understand, which is then passed to our discriminator in particular.
Once we've trained our character, we can then generate motions from the simulated character, and we can then take those motions and apply them to a high-fidelity mesh character, like the gladiator character that you see in the demo. And this is done by using Omniverse Kit, which allowed us to retarget the motions generated in simulation to the higher fidelity character. And it also allowed us to generate high fidelity renderings of the character to showcase the motions produced by our system.
So you can give it a prompt and maybe ACE generates a trajectory that's similar to what you want, but not exactly correct. So it's very quick when your interface is based on text, you can simply adapt your prompt and have ACE generate new trajectories. So just like a director reshooting scenes over and over again, controlling these animation systems with natural language leads to a much quicker iteration time, which should lead to intuitive, easy to produce results.
In our work, we develop a system called Adversarial Skill Embeddings, or ACE for short. And this is a system that allows us to train physically simulated characters that can perform a large variety of reusable motor skills.
ACE in particular is an approach for making physics-based simulations that are realistic and look human-like. ASE takes a dataset of reference human motions that one wants to imitate and can produce new, natural, synthesized behaviors that follow that reference motions in the physics simulator. The goal of trying to make ACE interqueryable with language is that anybody should be able to create high-quality animations with ACE, and people should be able to do it quickly.
When humans try to learn to perform a new task, they will very rarely learn things from scratch again. So if you know how to walk, I'm not going to relearn how to walk again if I need to do something new. So the idea for that is that we now want to develop a model that can learn reusable skills that we can then use to synthesize motions for new situations.
So for example, as you can see in the GTC demo, the agent's not just able to do these different low-level skills, but can apply it to accomplish different objectives, like knocking over a block, navigating to a given task, facing one direction while walking in a different direction. And the idea behind all of these is A, because the underlying low-level checkpoint is so capable, these are all very quick models to train, and B, because it's all operating in the context of a physics simulation, they're all lifelike, realistic, physically plausible behaviors.
My hope with this line of work is that eventually these natural language models will allow us to develop more accessible and expressive interfaces.
If you're able to control these complicated systems with an interface as universal as language, then it should be really fast to iterate, to explore, to experiment, and make this technology much more broadly accessible to everybody.
Of all the technologies at GTC, nothing brings them together like Toy Jensen, or TJ as we like to call him. And for TJ 2.0, the team challenged themselves to help make him more natural, intelligent, and engaging.
Back in spring GTC 2021, we created a virtual Jensen for about 14 seconds that showed up in the keynote. So when we came to the fall, we were thinking, well, what's next? What would be surprising for our customers and viewers? And what makes sense for the technology we're bringing to the world?
We wanted something that was, on one hand, fun, but also could be taken seriously. And then we explored a toy version of Jensen, hence the name TJ.
It was to showcase a completely AI-driven avatar interacting with Jensen himself. Toy Jensen is powered by a very complicated cloud-based computing infrastructure called UCF, Unified Computing Framework.
It starts off with automatic speech recognition, and then that gets sent to the big NLP, or natural language processing, which is 530 billion parameters. And then it goes to the Riva TTS, text-to-speech, and then that gets turned into a WAV file, and then that comes back to audio to face, which is piped into Omniverse. It's this amazing chain. It's all happening in real time, and all we see is this character that answers questions.
How do astronomers look for exoplanets?
Most exoplanets are found via the transit method.
For Toy Jensen, the big NLP, or natural language processing, is the brain behind his answer.
And the accuracy comes from how we tune the model to be able to optimize where we can search in a very particular area and minimizes the errors of such a large language model.
Hi.
With the fall, it was the first debut of Toy Jensen. We received a lot of great feedback. But for 2.0, we felt a few areas that can really make a big difference. His voice, which is very important, was drastically improved.
For GTC 2022, we wanted to have Jensen's timbre combined with the prosody, rhythm, and cadence of a virtual assistant. We asked Jensen to record some data, but we didn't have enough of the virtual assistant prosody that we were looking for. We have a model that allows us to combine someone's timbre.
It starts with my voice.
With someone else's prosody from very high quality personal assistants.
It starts with my voice.
It starts with my voice.
So we were able to combine those things together and create TJ 2.0.
What is synthetic biology? Synthetic biology is about designing biological systems at multiple levels, from individual molecules up to whole cells, and even multicellular assemblies like tissues and organs to perform specific functions.
Toy Jensen is unique because he has emotion. For TJ 2.0, we saw the opportunity to expand on this, and we now have Anim Graph working. So we had animation states that were driven through AI, piped through the animation graph while Toy Jensen was talking. We also implemented full face audio to face, which allowed the upper portion of his face to be driven through the WAV file. So when he talks now, he was more expressive.
Thanks, Jensen. I'm super excited to explain how I was made. Avatar.
One of the hardest things with conversational AI is the response times, the latency. If things slow down or the response is wrong, that's very frustrating. And that's a very hard thing to control still.
As we were implementing some of these new technologies into TJ 2.0, we had a few showstoppers where we had some serious performance degradation.
A lot of people look at real time as 30 frames per second. But for a really convincing performance, especially using things like audio to face, we really want to hit 40 to 50 to give you that detail that you would otherwise miss.
Eddie had to go in and figure out how to rebuild full face audio to face to get a performance improvement. So there was a lot of pressure on him to try to go in and create a full face audio to face that would function and work properly.
My dream of Toy Jensen is to go beyond just a Google search representation through an avatar. We should be able to collaborate with Toy Jensen to solve important problems in the world.
Hi, how can I help?
My daughter spends a lot of time coming in and out of my office, and she gets to see what I'm doing, and she has questions. And it really makes me realize how important a digital avatar will be for the new generation. It can be a character that she can ask questions and get non-biased answers back. She'll have a vehicle that she can talk to, a character. We're really excited about the avatar having this connection with the user.
See you in Omniverse.
Omniverse not only unites teams and technologies, but brings us closer to our partners. Today, more and more companies worldwide are discovering the power of this incredible platform to help solve their real-world problems.
Our collaboration with Amazon Robotics was about building a digital twin of a warehouse facility that Amazon plans to build. It's very practical to build a replica before you deploy something to the real world so that we can basically optimize it, train, and deploy the systems virtually before we actually do it in real life. What we did is basically help them set up their first digital twin using our Omniverse platform.
So with Omniverse, we've built kind of the ideal toolkit to construct the world before you can even simulate it.
And so what we did was we provided output, USD, and animations, and we also provided the SolidWorks, Revit, CAD files to the NVIDIA team.
For the CAD data that we have received from Amazon, we actually used our connectors that connect directly into Omniverse.
The connector is merely a way of translating the native representation of the 3D worlds inside each tool into a USD one.
A USD basically can contain all the data and all the information, which is something that previously was incredibly hard to do.
USD has been a key to actually helping us accelerate, and it's a fantastic building block.
On top of that, we also use pretty much all the range of DCC tools available to generate the rest of the content. So the artists are actually able to work within whatever they're comfortable with, and we're not asking them to change anything that they're doing, thanks to our connectors.
The most powerful things about the NVIDIA ecosystem of tools and technology is that our technical artists can use whatever tools they're comfortable with.
The beauty about using Omniverse is that it gave life to those applications that they have. It was a no-brainer that it made sense for us to collaborate on this project.
During the collaboration, the NVIDIA technical artists worked with our technical artists and helped get them to understand the tooling better and some of their practices.
We basically worked with them and showed them how it's possible to do things, like realistic material, realistic rendering, why the lighting is important, how to use the systems within Omniverse.
And it was a constant collaboration where every day they saw the improvements and the things that we have done. We've seen the experiments that they have done. We discussed it together, and then we made a decision how to move forward.
The autonomous drive, because it operates on sensors, needs actual photorealistic worlds to operate in and sense as it's moving around.
There's multiple components to it that go from all the way to the layout itself, where things are placed, as well as the navigation that the autonomous robots have to do, as well as navigation of the robots themselves. You can basically use the actual CAD data, and all of this data, once it's imported into Omniverse, can actually be rigged using our Isaac Sim system. And Isaac Sim is basically a platform within Omniverse for a robotic simulation system. So you can train them for ideal pathing and then rearrange the layout as needed.
We created a model based on synthetic data. And for a demonstration, we wanted to actually track the packages. So we added reflective tape to the packages, tried running them through, and that's when the model failed.
Omniverse Replicator, it is a framework to generate synthetic data in Omniverse. With synthetic data, in a matter of a day, you can generate a new packing material that is very reflective, that has different material properties.
Basically, what we did is that we had recreated an exact copy of all of their packages, which is something that, again, digitally you can do very efficiently and very quickly. So then they were able to train their perception system using a huge data set.
It was very easy for us to then go back to that synthetic data generation, and we added to our pipeline the ability to add reflective tape to the packages.
And then they were able to retrain the robotic arm, which then worked flawlessly.
The power of Omniverse and the fact that we were actually able, again, to collaborate within Omniverse and we're able to use all the tools we use without disrupting anyone's workflow, it all worked out in the end to be able to deliver the project by the deadline.
When they first saw it, when I first saw it, I was amazed.
My initial reaction was just wow.
Yeah, so I still remember this because it was incredible.
As a matter of fact, like every single meeting during that period, I guess we started it with a quiz. Like, is this real? Is this digital?
At NVIDIA, we've always believed that the sum is greater than its parts, and nowhere is that more evident in the work that we do with our partners. And the beauty is, we both commit our resources to it because we both know that we're going to get something out of it that's going to help everyone.
Just seeing that digital twin and the life that we were able to bring to it was phenomenal. Just knowing that we were able to impact the operation at Amazon, and we're continuously going to do that, I'm very proud of it.
The more we looked at the NVIDIA technologies, the more we realized it was satisfying other use cases, because it's not just providing one tool for us, it's providing an ecosystem of tools and technology that's going to help accelerate multiple areas for us.
We hope you've enjoyed this behind-the-scenes look at the passion, talent, and hard work that goes into GTC and every NVIDIA project, product, and production. We're always excited to share our body of work with the world and look forward to sharing even more. Thank you, and we'll see you at GTC this fall.